All right, so here we are at the last one in the section. Here we want to launch something straight up in the air, so still one-dimensional even though it's vertical. We have a starting velocity, and if you think about it, we have an ending velocity. So we'll talk about that in a second. And because the velocity is changing, the only thing we know to do about that right now is to say that acceleration is a change in velocity over a change in time. Now, in this case, we're looking for that time. So sometimes it helps to think about this as being over 1, and then you can cross multiply and then divide or rearrange. A few different ways to get from this formula to the one we're looking for. But ultimately, we'll find that our change in time ends up being our change in velocity divided by our acceleration. All right? And so let's think about this. We know when a ball reaches its maximum height, the ball, whether it's a football, volleyball, basketball, baseball, golf ball, anything, will go up in the air, and then for just a tiny fraction of a second, immeasurably short period of time, will almost seem like it pauses for just a second and then it comes back down. And that's because its vertical velocity goes to 0 before it turns into the other direction. And so we've actually got something similar to the last one, question 9, even though it didn't initially seem like it. But we've got some velocity, and then we want to see what happens when it gets to 0. As it turns out, the height doesn't matter here, as long as you're not like so high in the air that you're getting close to space and something there weird. That's a different sort of question. But as long as you're technically reasonably close to sea level, this is always going to work the same way. So it may seem like there's not enough information here because there's only one number in the question, and I'm supposed to ignore the other one and somehow get a new answer. And what we're going to have to pay attention to here, and something that we're going to think about a lot in this class, is where this acceleration is going to come from. So if you throw something in the air, it comes back down because of gravity. And so gravity, as it turns out, is a special acceleration on objects that are on Earth at roughly sea level. So technically, it's a very specific number, a very special case, and works almost nowhere else in the entire universe. But thankfully for us, it does work where we are, and we know what this number is, and this is what we do, right? So we can plug in, we can find an answer. We've got everything we need. I don't know the change in time, which may seem like we're off to a bad start, but this is the thing we're looking for, so hopefully no big deal. The change in velocity, here, I don't want to think about time being negative. I'm not worried about directions or anything. I just want to know how much time. So you think of it as being like magnitude again. So 1.39 meters per second. Then gravity is the acceleration. It shows us, how quickly the ball would come back down or how it's changing the velocity, depending on the type of question. And so that's going to plug in for the bottom. So technically 9.80, sometimes you see 9.81. We're just going to cut it, call it 9.8. Now the units do something a little bit funny. We've got meters per second squared on the bottom. And so, I think it's clear that the meters and the meters will cancel, and the seconds here will partially cancel with this one. You have to be careful because this one's divided under the division, and so it does this weird kind of like flip and multiply thing, and it just turns back into seconds, which, is good because ultimately that's what we wanted. Right? So a little bit of a weird path to see the units and how they line up, but it's there. Then now, I'm going to go ahead and evaluate. So running those through a handy-dandy calculator, because the answer is relatively small, this one's set to 4 decimal places on the answer, and it looks seconds.